Hey guys, it's Mr. Katz. Just wanted to go through the answers to the proof videos. I'm going to go through them pretty quickly. I'm not going to write everything down, so listen carefully. I just didn't want this to be a 30-minute video. But these are the answers to page 79, 80, and 81. And this will also kind of help you work through proofs. Remember, not only are we learning how to prove things about quadrilaterals, but as we prove them, you should also memorize the actual property because they exist for every single quadrilateral. So this is page 79. And basically what it says is that if you have a parallelogram, we want to know if all diagonals bisect each other. And they do, and we could prove that. And here's how you prove it. First of all, in order to prove that diagonals bisect each other, you technically would have to do, we'll call this E right here. You definitely would have to prove that AE and CE are the same distance apart. So that would mean that this is bisected. And then you also would have to prove that DE and BE are bisected. We're only going to do one of them because they're pretty much the way you prove the first set, and we're going to prove the green line is bisected, the green diagonal is bisected, and then you pretty much would do the same thing to prove the red line. It would just, you would use different angle numbers and use different sides. So first of all, we are given that ABCD is a parallelogram. And then if that is, our next line could be that all the different sides are parallel. So I put that right here. And if the sides are parallel, I gave these little angles right here. I'm focusing on this triangle right here and this triangle right here. Because if we could prove those triangles right here and right here, these little ones, are congruent, then we can then prove that, excuse me, that this is going to be congruent to this because of CPCTC. So first of all, angles 1 and angles 2 are congruent because if you look at 1 and 2, if these are parallel lines, then 1 and 2 are alternate interior angles. And 3 and 4 are also alternate interior angles. So 1 and 2 and 3 and 4 are both congruent to each other. So I'm going to go ahead and mark those. And again, both was the alternate interior angle theorem because we already know we have parallel lines. So we have at two angles, and actually because it's a parallelogram, I can say that side AD is congruent to side BC, or their measures are equal. And that's this right here. And that is because that's I'm not writing the reasons, but that would be the property of a parallelogram, that opposite sides are congruent. So based on this line and this line, this triangle, which is ADE, is congruent to triangle BEC. And the reason for that is you have angle, side, angle. And if the triangles are congruent, AE, line AE and line CE are actually parts of those triangles. That they're congruent. And not only are they congruent, those are the diagonal, the parts of the diagonal. So now after you prove that and after you do the same thing with the other diagonals, you can say that we've just proven the diagonals bisect each other because we've proven that this side and this side of the diagonal are both congruent because of this is because of CPCTC. All right, so the next one, I'm not going to do a complete proof, but I'm going to give you the idea, so I hope that you can turn this into a two-column proof. Basically, if you're given the information that the diagonals bisect each other, I threw that in right here. You can see that this side is congruent to this side is congruent to this side. So I'm going to focus on this triangle right here and this triangle right here. And if you have these two sides already congruent to these two sides, you could see that angles 4 and angles 5 are vertical angles, so they're going to be congruent. Well, that proves that these pink little triangles are going to be congruent because of side, angle, side. Well, if the pink triangles are congruent, that would mean, and I hope you can see right here, that angle 2, which is right here, is congruent to angle 3 because of CPCTC. Well, once you know angle 2 and 3 are congruent, you can then say that those are alternate interior angles based on these parallel lines. Well, that would mean that the green lines are going to be congruent because of the converse of the alternate interior angle theorem. Then you could essentially do the same thing for the other side. So now we're going to focus on these two yellow triangles right here. These triangles are also congruent because of side, angle, side, side, angle, side. So once you know that these are congruent triangles, you can say that 6 and 7 are congruent. And if 6 and 7 are congruent, then you can say, since those are alternate interior angles based on these yellow lines, that these yellow lines are parallel because of alternate interior angle theorem. But once you prove that you have two sets of parallel lines, you have thus proven that you have a parallelogram. All right, guys, in this proof, this is, I believe, number one on page 81. So in this proof, this is the information you're given. These are parallel, and these two sides are equal, and these two sides are equal. So I'm going to draw a diagonal in and be able to prove that. See, if I want to get that this is a rhombus, I'm going to basically prove that this is a parallelogram. And if it's a parallelogram, opposite sides are congruent. So that would mean they're all going to be the same, which means it's a rhombus. So if I go ahead and draw in this diagonal, you already have side, 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 and this side is congruent. So now you can prove that this triangle is congruent to this triangle. So if you do that, you can actually prove that this angle and this angle are congruent, which you already knew. And then you can prove this angle and this angle are congruent because of CPCTC. And if you prove that those angles are congruent, it actually proves this line right here, is also a parallel line. So now you've proven it's a parallelogram. So if you prove it's a parallelogram, that means not only is, AD congruent to AB, because that was the given, but now you know that AD is congruent to BC, because in every parallelogram, one of the properties is opposite sides are congruent. So if AB is congruent to AD and AD is congruent to BC, we can put that together and know that AB is also congruent to BC. And what you've just proven is that every single side is congruent. So you could actually, not only were these congruent to each other, but they're also congruent to the other two. And now you've proven it's a rhombus. Here you're given that it's a rectangle. And remember, definition of a rectangle is you have 4 right angles. But we're going to leave these out for a second. We also know M is the midpoint, which means that that is congruent to that. And then since it's a rectangle, we also know that a rectangle is a parallelogram. And in every parallelogram, opposite sides are congruent. So now you have these two triangles are congruent because of side, angle, side. And if they're congruent because of side, angle, side, you have then proven that this side of the triangle is congruent to this side of the triangle. And if this triangle, this big triangle right here, has two congruent sides, it automatically makes it isosceles because of the definition of isosceles. All right, guys, so this one I think was the hardest one of all of them. The information you were given was that this is a angle bisector, so 1 and 2 are congruent. I'm just going to use equals, and I'm not going to put the angle measures. I just want you to see my reasoning here. So if 1 and 2 are congruent, I'll write that, and then it says 3 and 4 are congruent. Okay. We also know that this is a parallelogram. So all these are parallel, these are parallel, these are parallel, and these are parallel. Okay. So we already know that, and we're basically trying to remember, we're trying to prove that. Let me make sure I get this right. This right here is a parallelogram, this little small guy right in the middle. Okay? Well, if we prove that all sides are parallel, we can prove it's a parallelogram. Well, we already know one of the sides is parallel. We know this side because the whole thing's a parallelogram. So we have one of the sides. So we basically have to prove these diagonal lines right here are parallel to each other. So if I can get 6 and 4 to be same side interior angles, I'm sorry, they are same side interior angles. If I can get 6 and 4 to equal 180, I'm going to basically have that these lines are parallel. If I can get, alternate interior angles somehow, or corresponding angles somehow, I'll be able to prove that they equal 180. Right? So 1 and 2 are equal, and I know that 1 and 6, because of these parallel lines, are same side interior angles. So I know that 1 plus 6 is equal to 180. What else do I know? I also know 6 and 8 are equal to 180. I don't know if that's going to help me because they're a linear pair, but angle 6 and angle 8. 4 and 7 are going to equal 180 degrees because, again, the 4 and 7 are same side interior angles. And I also know that 5 and 7, because they're a linear pair, will equal 180. And again, I don't know if any of this is going to help, but you never know. Also, what I know is because this whole thing's a parallelogram, if you add 3 plus 4, it's going to equal 1 plus 2. And remember, all I'm doing is brainstorming. I'm just looking for things that I can say that's true about this figure. I can also say that 4 and 5 are alternate interior angles because those lines are parallel. So 4 is equal to 5. And I also know that 8 and 1 are going to be congruent. Okay? Well, somehow I need either 6 and 4 or 1 and 7 to equal to 180. So I want to start messing with 4 and 6 a little bit. So let's see. I see a 6 right here. I see an 8. Is there any relationship between 4 and 8? And I don't see one. I see that 3 and 4 equals 1 plus 2. And I can use, let me see if I can manipulate this data in any way, shape, or form. 1 equals 2 and 3 equals 4. Well, if I take this line right here, I can actually say, since 3 and 4 are the same, I can say 3 plus 3 is equal to, instead of 1 plus 2, since 1 and 2 are equal, I'm going to say 1 plus 1. Well, if 3 plus 3 equals 1 plus 1, you can understand how we know that 3 and 1 are going to be congruent, because 2 times 3 equals 2 times 1, or 2 1s together. Angle 1 plus angle 1 is congruent to angle 3 plus angle 3. That means that these have to be equal. So if 3 and 1 are equal, is that going to help me in any way? I don't know. Let's see. Instead of 4 equals 5, I can say 3 and 5 are congruent. What about 4 and 5? Well, we already know 4 and 5 are congruent. So we have 5 plus 7 equals 180. I have 4 plus 7 equals 180. Is anything else equal 180? 1 plus 6 equals 180. All right. Well, how about this? Since 1 plus 6 equals 180, and 1 and 3 are exactly the same, I could pretty much say 3 plus 6 equals 180. I'm using this line right here, and my newfound information that 3 equals 1. Well, remember that 3 and 4 are exactly the same. So instead of 3 plus 6 equals 180, I could substitute it in a 4, and I've just proven that 4 plus 6 equals 180. And remember we said in the beginning, if 4 and 6 equal 180, that means angle 4 and angle 6 are supplementary. Well, they're also same side interior angles. Well, by 4 and 1 6 being supplementary, I now know that this is parallel to this line. And now you have pretty much 2 sets of parallel lines. I've proven that this is a parallelogram. And that is all of them. I think that this one is confusing, but what I did was I just wrote down as much stuff that's true as possible, and I always kept in mind that I was trying to get 4 and 6 to be supplementary. So I was looking for things that equaled 180, and every one of these statements that I wrote here is actually a true statement. Okay, no, don't forget I didn't write measure of angle 6 plus the measure of angle 8, but you know we should have done that in a real proof. So now I would go back and reorganize and figure out a way that I can write this a little neatly in order with things that I needed. Okay, and just a reminder, then the very beginning, I did automatically know that this line was parallel to this line because that was in the given that it was the whole thing was a parallelogram. And then all I did was I proved that this line was parallel to this line by using the converse of the same side interior angle. I proved that 4 and 6 were supplementary, and then that would mean that the green lines have to be parallel because of the converse of the same side interior angle theorem.